Good afternoon, and welcome to Hand-Wavy Chemistry, where we do not delight in the details, but rather bask in the big picture. Yesterday, as I was walking the kids to school, they started to lag behind. I turned to them and I called out, "You're moving slower than molasses!" Which actually made me think of the longest continuous running experiment in the world, the pitch drop experiment. This experiment began in 1927 when hot pitch was poured into a funnel. 3 years later, when the pitch had cooled, they cut the neck of the funnel so that it could begin to drop down through it. Pitch has an incredibly high viscosity, meaning that it does not flow very fast, and it takes years for a drop to form and to fall. In fact, since the experiment began, there have only been 9 drops that have fallen from the funnel. And we expect that the 10th drop will fall within the next 8 years. This next to me is not actually a still image, but rather a video feed of the experiment, as it is live streamed 24 hours a day throughout the world. So you can tune in and wait for that drop to fall. But if 8 years is too long for you, other highlights to watch out for include somebody changing the battery on the clock, people, members of the public, stopping by to look at the experiment. But why is it that everything here is flowing so slowly? When molecules come together, there are interactions between them. We call these intermolecular forces. These interactions can be positive, attracting them together, or negative and pushing them away. When these molecules come together, the lowest energy state will maximize the number of positive interactions and minimize the number of negative interactions. If these interactions are sufficiently strong, then the molecules become locked in place, and we call this a solid. The molecules can no longer move past and around each other, and instead can only vibrate. If the interactions are not strong enough to lock the molecules in place, then they can start to slip past each other and move and flow. And this is a liquid. And if the interactions aren't even sufficient to keep the molecules near each other, then there will be big distances between them, large gaps between the molecules, and we will have a gas. So depending on the types and strengths of the interactions and the energy of the molecules, we could have a solid, a liquid, or a gas. So in the case of something like pitch, there are a lot of interactions that are slowing the movement of the molecules past each other, but they're not strong enough to lock everything in place. I mentioned that when the experiment began in 1927, they used hot pitch to fill the funnel. That is because by giving the molecules more thermal energy, they are more easily able to overcome the forces trying to hold them in place, and they can begin to slip and flow more easily. There is another tragic story about molasses, and that is the Great Molasses Flood that happened in Boston in 1919. A large tank filled with molasses ruptured and burst, sending a massive wave of the material through the streets at speeds of around 50 kilometers per hour, killing 21 people. There are multiple reasons why the tank failed. One of which is in relation to the extreme temperature swings that were occurring at the time. There were below freezing temperatures. When the tank was being filled, they warmed the molasses so that it could flow more easily, just as scientists warmed the pitch so they could fill the funnel. The thickness of the tank has since been determined to be too thin for the amount of molasses inside. And finally, as the temperature changed throughout the day, the materials would have changed in volume. They can expand or contract depending on if it is heated or cooled. Ultimately, the tank ruptured. But why did the molasses flow so fast? Well, this comes down to force. That amount of molasses has a large force of gravity pulling down on it. And when you push a fluid, it usually will flow faster and quicker. And so this massive weight of molasses, suddenly freed from its tank, could force its way down the street. Interestingly, not all fluids behave this way. There are a class of materials known as non-Newtonian fluids that do not flow faster when you apply force to them, but rather flow slower. But that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.